Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 2, Lesson 3 on function composition. That sounds kind of interesting, so let's jump right into it to figure out what it means to compose two functions. Now let's talk about inputs and outputs to functions. Functions take the value of an input variable and return the value of an output variable. So it stands to reason that this output, the thing that's coming out of a function, could then be used as an input to a second function. This process is known as the composition of functions, and it often occurs in real-life problems that involve multiple steps to arrive at a final answer. So you've done function composition whether you kind of knew it or not, because it's often the case that in multi-step problems, you might take some number and throw it into a formula or something like that, an equation, get an answer out, and then take that value and do something with it in another formula. So let's take a look at that in exercise number 1. Jonah is taking a road trip where he drives his car at a constant speed. The distance he has driven is given by the function d of t equals 65t, where t is the number of hours Jonah has been driving. His car gets 30 miles per gallon of gas he uses. So the function g of d equals d divided by 30 gives the gallons of gas he uses as a function of the distance in miles he has driven. Letter A. How many gallons of gas will Jonah's car use after he has been driving for 3 hours? Show the calculations that lead to your final answer. All right, so what I'd like you to do is pause the video now and see if you can figure out how much gasoline Jonah's car will have used after he's driven for 3 hours. Everything that you need is up here. Pause the video now and see what you can do. All right, well, here we go. And obviously you may want to use your calculator a little bit on this, but the first thing I'm going to want to do is simply figure out how far Jonah has driven in 3 hours. Now that's given by the function d of t equals 65 times t. So first things first, I'm going to figure out the distance Jonah has driven. That's going to be 65 times 3. This one I think I can do in my head. That's going to be 195 miles. All right, now that's just simply how far Jonah has driven. To figure out how many gallons of gas that he's used, I'm now going to use the function g of d equals d divided by 30, where now my input is 195 miles. So I'm going to figure out what g of 195 is, and that's going to be 195 divided by 30. And as much as I love arithmetic, and I do love arithmetic, for this one I think I'm going to do 195 divided by 30. And I'm going to figure out that that takes 6.5 gallons of gas. All right, let's pop back into our full screen. Come down here. Now, kind of a simple idea. In letter B, it says to draw a diagram to represent the inputs and the outputs of the two functions. Simple enough, right? The whole idea here is that t equals 3 kind of went into this function d of t, right? And what came out of it was d equals 195. That input then went into this function g of d, right? And what came out was 6.5 gallons. And it makes all the sense in the world, right? Functions take an input and they give an output. Sometimes that output can then serve as the input to another function if it makes sense. And it oftentimes does in a real world setting. A lot of times this could make sense if you had some kind of in geometry, some kind of geometric formula for, let's say, the area of something or the volume of something. So you could very easily see taking, let's say, the radius of a circle, putting it into the area function for a circle and getting the area of the circle out, and then using that area for some other calculation, right? And it's kind of like a domino effect. A value of x goes in, a value of y comes out, maybe that value of y goes into another function as the value of x, and then another one comes out, etc. And you could compose as many functions in a row as you so chose. In this particular lesson and in this course, we're going to mostly be sticking with the composition of just two different functions. So let's take a look at that a little bit more. Now, composition notation. There are two notations that are used to indicate composition of two functions. These will be introduced in the next few exercises using various representations of functions, i.e. the equations, graphs, and tables. All right, the two function composition notations, one of them, in my opinion, is very straightforward. The other one is a little more confusing, but some of you may have used it in geometry. We didn't use it in the E-Math Instruction Geometry course, but I do know that some teachers do use it, so for those of you, you might have a little bit of a leg up in this other type of notation. But let's get to it in exercise number 2. Given f of x equals x squared minus 5 and g of x equals 2x plus 3, find values for each of the following. Letter A, f of g of 1. All right, so I love this notation because to me this is very straightforward. I have an input of 1 that's going into function g, and it's got some value, and that value is g of 1. And then g of 1 is going into the function f, and it's got some final value. So there's no question in my mind in this particular notation, all right, I first need to figure out what g of 1 is, and that's 2 times 1 plus 3, which is going to end up being 5. And then I need to figure out what f of 5 is, and that's going to be 5 squared minus 5, which is 25 minus 5, and that's 20. All right, so at the end of the day, f of g of 1 is 20. And it's kind of cool because the input of any function just sits inside of those parentheses that's right beside the function. So the 1 sits right beside g of x, so g of 1, right, has a value, it's 5. And then 5 sits inside of the parentheses right beside f, and f of 5 is 20. All right, let's do another one of these together. Letter B. G of f of 2. All right, so in this case, now 2 is sitting inside of f, and then f of 2 is sitting inside of g. So if I want to know what this value is, the first thing I want to do is figure out what the value of f of 2 is. And that's going to be 2 squared minus 5, which is 4 minus 5, and that's equal to negative 1. And then I want g of negative 1, which is going to be 2 times negative 1 plus 3. That's negative 2 plus 3, and that's just equal to 1. So g of f of 2 is equal to 1. Now letter C might be looking a little confusing. G of 0. That's okay, right? G of 0 is a value, whatever it is, and then that value is going to go back into g again. And that's okay. You could have like a function, and there are real world examples of this, right, where you kind of get like a feedback loop. And output comes out, it goes back into the original function, sits out another output, that goes back into the original function, etc., etc., etc. See if you can figure out what g of 0 is. All right, well, g of 0 is 2 times 0 plus 3. That's going to be 0 plus 3, which is 3. And then g of 3 is going to be 2 times 3 plus 3, which is 6 plus 3, which is 9. All right, so g of 0 is 9. Now, I love this function notation, and I kind of wish that all textbooks and all math courses use this function notation and only this function notation. But for some nearly inexplicable reason, that's not the case. Many, many times, this next type of notation is used. I restated the functions down here so that we didn't have to kind of keep scrolling back up to see them. Now here, the way I would read this is f of g of negative 2. And the reason that I don't love this notation is it's not entirely clear from looking at it which function the negative 2 goes into first. And it may even seem, because you're reading it as f of g of negative 2, it might seem, oh, I should put it into f first, and then that should go into g. And unfortunately, that would be wrong. In fact, the way that this works is that the negative 2 goes into the g first, and then the output goes into the f. All right, and that's a little bit unfortunate because especially when you read it this way. It's this notation, though, that you may have seen in geometry. So some teachers may have shown you something that looked like this. You know, something that looked like that, which would mean that you would take this point, you would reflect it in the x-axis first, and then you would translate it in some way that I didn't specify here. All right? So if that kind of looks familiar to you with the little, what looks like a little O or a little circle, it makes sense. Anyway, once you actually know that, then these problems are exactly like they were before. The first thing I want to do here is figure out what g of negative 2 is. So g of negative 2 is going to be 2 times negative 2 plus 3, which is negative 4 plus 3, which is negative 1. And then that negative 1 goes into f, and f of negative 1 is negative 1 squared minus 5, which is 1 minus 5, and that's negative 4. Okay? That's it. So the thing that's, again, confusing about this particular notation is just understanding that when I do something like g of f of 3, then what's going to happen is that that 3 first goes into f, and whatever then comes out goes into g. So what I'd like you to do now is pause the video and see if you can figure out the final values for both e and f. All right, let's do it. So for letter E, do that, that'll work. First thing I need to do is figure out what f of 3 is. That's going to be 3 squared minus 5, which is 9 minus 5, which is 4. And then I need to know what g of 4 is. That's going to be 2 times 4 plus 3. That's 8 plus 3, and that is 11. Now in letter F, it doesn't really matter which one you think about first because they're both f. That's f of negative 1. Technically speaking, the negative 1 should go in here, and then the output should go in there. But of course, it really doesn't make any difference given that they're identical functions. So f of negative 1 is going to be negative 1 squared minus 5. That's 1 minus 5, which is equal to negative 4. And then f of negative 4 is going to be negative 4 squared minus 5, which is 16 minus 5, which is 11. Which is exactly what I had for letter E. But that's a total coincidence. That has nothing, these two 11s have nothing to do with each other. Last thing I want you to do is think, hey, every composition problem ends in 11. Definitely not. All right, so the rest of this worksheet is really going to be kind of stressing these ideas. Now, we should always be ready to work with functions in any one of their many forms, including equations, tables, and graphs. Up to this point, with composition of functions, we've only used equations, and they're the most common way functions are represented. You know, they're not necessarily the easiest things to use, though. Now, let's look at a problem where we've got both a table for f of x and a graph for g of x. Let's take a look. Given the two functions below, evaluate each of the following. Awesome. And not only do we have all these things, right? We've got them, and we've got the two different types of function notation. So let's do letter A together, all right? And then maybe have you work on the rest of them on your own. So letter A says f of g of 1. So the first thing I have to do is I've just got to figure out what g of 1 is. Now, g is represented by this graph, so I go over to x equals 1, I go up, and I find because the point 1 comma 6 lies on this graph, g of 1 is equal to 6. And now the great thing is that g of 1, which is equal to 6, is the input to f, so I'm just looking for f of 6. And f of 6, there's my input of 6, f of 6 is equal to 0. All right, that's easy. In fact, this problem should be much faster than the last one because you're either just looking at a table, which is exceptionally easy to find the outputs for a given input, or you're looking at a graph, which is a little bit more challenging, but still probably faster than an equation. Why don't you pause the video now and see if you can do the rest of these, B, C, and D. All right, so let's do B. G of f of 4. The first thing that I want is I want f of 4. So f of 4, here's an input of 4. My output is 2. Now I want g of 2. So again, I have to come to my graph, go to an x equals 2, go up here. I've got the point 2, 7, and so g of 2 is 7. All right. Now we've got the little bit more funky notation, letter C, right? I've got g of f of 6. The 6 needs to go into f. Whatever comes out needs to go into g. So f of 6, looking at my table, here's my 6. So f of 6 is 0. And g of 0 is going to be 3. So g of f of 6 is equal to 3. And now that final one, g of 4, just to kind of emphasize that you can compose the same function. 4's got to go into g, and then whatever comes out of that has to go back into g. So g is my graph here. I'm going to go over to 4. I'm going to come up. I'm going to find g of 4 is equal to 3. Then g of 3 is right here, and that's equal to 6. So g of 4 is equal to 6. All right, that's it. I love doing these kind of problems with graphs and tables because they tend to be very, very quick. And we like things that are fast, most of the time. Anyway, formulas for function composition. On occasion, we will want to create a formula for the composition of two functions. We will see this facet of composition throughout the course as we study functions. The next two exercises illustrate the process of finding these equations with simple linear and quadratic functions. So, let's take a look at exercise number 4. Given the functions f of x equals 3x minus 2 and g of x equals 5x plus 4, determine formulas in simplest y equals ax plus b form for a, f of g of x, and b, g of f of x. All right, I just got to get all my letters in the correct order somehow. Thank God we don't go all the way to part x of any problem. All right, so in letter A, we're looking for f of g of x. Well, if it was f of g of 7, let's say, I would take 7 and I'd put it in g and I would get out 5 times 7 plus 4. But I don't have that. I have f of g of x. So I'm going to put x into g, and what I'm going to get out is 5 times x plus 4. So now I'm looking for f of 5x plus 4. And I know that looks a little bit weird, but keep in mind what function notation really tells you. Function notation, let's look at f. f of x equals 3 times x minus 2. Now what it appears like that's saying is that I should take x, multiply it by 3, and subtract 2. But what it really says is take the input, multiply it by 3, and subtract 2. You might say, isn't that the same thing? Well, here's what I mean by thinking about those in subtly different ways. The function is taking the input, multiplying it by 3, and subtracting 2. So if the input is more complicated, 5x plus 4, all that says is take the input, multiply it by 3, and subtract 2. And now I just have to do a little bit of algebra, 15x plus 12 minus 2. And that tells me I get 15x plus 10. So that is a formula for f of g of x, 15x plus 10. See if in letter B you can come up with a formula for g of f of x. All right, let's do it. Well, g of f of x is the same as g of 3x minus 2. In other words, f of x is 3x minus 2. I'm just putting it in there. Well, what does the function g do? The function g takes the input, multiplies it by 5, and then adds 4 to it. So when I do that, I'll get 15x minus 10 plus 4, and that will be 15x minus 6. By the way, notice that when we composed functions in this direction and composed the two functions in this direction, the two formulas were different, meaning that the composition of two functions is not commutative. Not commutative. The actual order that you compose functions in matters. All right. Now, exercise number 5. Test the formula you arrived at in exercise 4b by evaluating g of f of 3, both using the formula you found and by finding the value of f of 3 first. All right, so just getting all those formulas here, right? I want to know what g of f of 3 is, and I want to test to see if I got the formula right by first just doing g of f of 3 the way that we were doing it earlier in the lesson, and then just trying to use this formula for it. So let's go through this together. First, let's do this the way that we had been doing it at the beginning, right? So in other words, f of 3 is going to be 3 times 3 minus 2, which is 9 minus 2, and that's 7. And g of 7 is going to be 5 times 7 plus 4. That's 35 plus 4, and that's 39. So in other words, doing it that way, g of f of 3 is 39. But we now have a formula for g of f of x, so let's now use this one. If we do it this way, g of f of 3 is going to be 15 times 3 minus 6, and that's 45 minus 6, and that's also 39. All right. And the idea here is that even though you could do composition by going through these two processes, first figure out f of 3, then figure out g of 7, it's kind of nice to have a formula where we can combine the two actions of the functions into a single function. All right, into a single function. Let's do one more like this that's a bit more complicated. Exercise number 6. If f of x equals x squared plus 12, and g of x equals x minus 5, then f of g of x equals one of the following. All right, what I'd like you to do is pause the video now and see if you can figure out which one is the correct choice. All right, well here you would get a huge difference depending on which direction you compose these two functions in. So let's be very clear, right? X goes into g, and what comes out is x minus 5, and then I want x minus 5 to be going into f. So f of g of x is f of x minus 5. Now what does f of x do? Well, it takes the input and it squares it. Takes the input and it squares it, and then it adds 12. Now, if this was one of those four choices, just obviously one of those four choices, that would be the correct answer. Boom, done, got it, right? It's not one of these correct answers, so I have to do a little bit of algebra. I'm going to have to multiply this out, right? So I'm going to have x minus 5 times x minus 5, and then I can't forget the plus 12. That's going to be x squared minus 5x minus 5x plus 25. Can't forget the 12, plus 12. That's going to be x squared minus 10x, and then 25 plus 12 is 37. All right, so if you got choice 4, then you definitely know what's going on, at least in these types of problems. All right, let's wrap this up. Okay, so today we talked about function composition, and I hope that at its base level, this makes a lot of sense. Even if the notation is a bit confusing, even if you're using it with these different forms and coming up with formulas at the end is a little confusing, I hope the general idea makes sense. You know, functions take values of x and give values of y, right? So it makes sense that I could have multiple functions. I throw a value into one of them, it spits out an output, I take that output, I throw it into another one, it spits out an output, and I could just kind of keep that domino effect going, right? And that's what this whole lesson is today. You'll have to grapple a little bit with the different types of notation on the homework, but hopefully you'll kind of get used to them through that process. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.